a sequence is like a list of terms. So 2, 3, 4, 5, so on. It could be finite or infinite. Also, it can be written like this. So this is like term A1, term A2, term A3, all the way till AK. This is how you represent this. It doesn't have to start from 1, and it can go all the way till infinity as well. There are two special types of sequences. One is the arithmetic sequence. So it's like there's a term, let's say 3, and then the next term is 3 plus some constant number. So let's say 3 plus 4, 7. And then the next term would have plus 4 again, 11. It could either be infinite or finite. And we represent in each term, let's say this is n is equal to 1. Another, this is n is 2, n is 3, n is 4, and so on. You can represent it like this. A1 is the first term. And the second term, A2, would be, instead of writing this, I can rewrite it like this. A1 plus A difference. So plus 4 in this case. Then the next term could be written as plus 2D. So plus 4 plus 4. And then the next one would be written as 3D and so on. So for a particular term, an, it would be equal to the first term plus n minus 1d. This is the formula for a particular term in a sequence. And if it follows this pattern where a constant is being added, then it's called an arithmetic sequence. Similar to sequence, we also have series. But let me represent another sequence, then I will go to series. So the next one is geometric sequence, where there's a ratio, a constant ratio being multiplied. So A1, and then you have A1 times R. So the previous term times R. A1 R cubed. Of course, this follows a pattern of an A1 R to the power of n minus 1. So an example of this would be 2, then R could be 3. So 2 times 3 is 6, and then 6 times 3 is 18, and then times 3 again, times 3 again, 1, 6, 2, and so on. We have a geometric sequence where a term is represented like this. We have an arithmetic sequence where a term is represented like this. Like sequences, we also have series where each number is being added. So in a series, we have A1 plus A2. The terms are basically being added, plus A3 and plus A. Okay, so a series is represented like this. So in arithmetic sequence, arithmetic series, A1 plus it with A1 plus D, and then plus that with A1 plus 2D. If this series goes to infinity, then the total sum, let's call it S would go to infinity. So an arithmetic series would only exist if terms are finite. Instead of adding them all one by one, we can calculate the series by a simple formula. So I can also represent S in reverse. So A plus n minus 1d. So this is the last term. And then this is the second last term. And then this is the second term. And then this is the first term. If I add all of them together, I get 2s is equal to, for the first one I have 2 times first term plus it with n minus 1d. For the second one, I also have 2 plus the first term, and then d plus n minus 2d, which is n minus 1d. So this and this makes this. Also, you may notice that these two look exactly the same. For the third one, it will also be 2a1 and then plus 3d, plus it with n minus 2d, which will give n minus 1d. So basically when we are adding them, this plus this, this plus this, this plus this, and so on, we get the same value being added a particular number of times. But this makes sense because a1 is being added twice in each term. We are adding the first and last. It's always going to be n minus 1d. If we go to the next term, let's call over here, a 1d gets subtracted. Over here 1d gets added, so the sum is basically the same. Since there are n terms in total, we can write d, and then s is equal to n over 2, n minus 1d. Now let's do a series for a geometric one. Geometric series. Last time I said an arithmetic series has to come to an end, otherwise if it goes to infinity, the sum would go to infinity, even if it's like 0.001. But geometric series is different. You have 1 and then divided by 10. So the ratio is 1 over 10, and then 1 over 10 again, and 1 over 10 again, and so on all the way till infinity. If we add them all up, what do we get? This goes all the way to infinity, so this is equal to, you have 1 point plus 1 1 1 1, so it's a 1 plus 0.1, which gives 1.1, and then plus 0.01, which gives this 1.11, and so on. Basically what I'm saying is, for a geometric series, even if the series goes to infinity, you can still get a finite number. This only works if r is between -1 and 1. So a1 plus a1r. If r is between -1 and 1, then this term would be smaller than the previous one. R square. This goes to infinity and we get s. And then if we have rs, then it's a1r plus a1r squared plus cube, and so on. Well, let's assume the series is finite. And then we can, this and this are same, this and this are same, this and this are same, except for a1 and a1rn. Every term is being repeated in both s and rs, so we can do s minus rs. This and this would cancel out, this and this will cancel out, and we would be left with a1 minus a1rn. And then so the sum is the first term times it by 1 minus r to the power of n over 1 over r. Now if this n goes to infinity, then we have this first term divided by 1 minus r. If n goes to infinity and r is between -1 and 1 only in this condition, then this will go towards 0, and then a1 times 1 is a1. So this is the formula we get.